Assalamualaikum and a very good day to everyone. So today we will continue our next topic in our EMT courses, which is regarding on the time varying field and Faraday's law. So the objectives of this topics or chapter are we need to identify the difference between the static field and the time varying field. So in this chapter onwards, we are no longer discussing about or talking about the static field. We will discuss and deal with the time varying field, okay, where time will be involved in the existence of the field, yeah, and also to exhibit the phenomena whereby the current is produced by the time varying magnetic field, example Faraday's law, and investigate on the changes of Maxwell equation for the time varying field due to Faraday's law. Okay, so before that, so let's discuss about what is a time varying field. Okay, so let's has a bit recap on what we have learned so far. So far we have learned about the magnetic field. Okay, magnetic field and also the electric field. Okay, electric field. But both of this field, it is a time constant, meaning that it doesn't involve time. Okay, so when we discuss about both of the field, we only consider the x, y, and z for the Cartesian, okay, and for the magnetic as well, we only consider about the x, y, and z axis only for Cartesian. All right. It doesn't involve of time changing. All right, so now in this topic or in this chapter, our field source will be same. We're going to be electric field and magnetic field. It can be electric field or it can be as well magnetic field. However, in this chapter we will start considering where the time now will be changing as well. Okay, the time will be vary, okay, and will then, of course, it will affect the electric field and the magnetic field that is formed. All right. So there are two important issues in time varying fields that we need to look at. So the first one, what we're going to discuss today is regarding on the Faraday's law, and another one is regarding on the displacement current. So this we're going to look on the next lecture. All right, and we're going to see based on these two issues, all right, how does it will modify our Maxwell equation that we have learned so far. So let's have a bit recap on what our Maxwell equation that we have learned so far. So far you have been introduced with the divergence of D is equals to rho V. So this is in electric field, okay, static electric field. And second one is, so this is the first one, and the second one is regarding on the integrations of E dot dl is equals to 0. So this is in integrations form, whereby we can write also as well in point form, which is curl of E is equals to 0. So this is for the electric field. For the magnetic field, okay, you has been introduced the closed integration h dot dl is equals to I enclosed, okay, I enclosed, where it also can be write in a point form of divergence of h is equals to j, right? And the last Maxwell equation, the fourth Maxwell equation that has been introduced to you guys is B dot ds is equals to 0, whereby in a point form it can be rewrite as divergence of B equals to 0. So these are the Maxwell equations that is regard electric field, static electric field, and static magnetic field. So we will then look what we're going to affect or how the Maxwell equations will be affected when we are discussing the in time varying fields conditions, right? Alright, so now let's look what is Faraday law basically. So Faraday law has been developed by Mr. Faraday, okay, on after 10 years of scientific research. Yeah, so what he basically found, okay, he said that generation of electric current, okay, is due to the time varying magnetic field, meaning that when there is a time varying magnetic field happen, okay, it will be generating electric current. Okay, for example, in this demonstration, okay, so this is the demonstrations of Mr. Faraday's experiment. So he found that when there is a magnetic field, okay, so when there is a battery supply, okay, to these primary windings, okay, which has been I would discuss this in last lecture, right? When there is a when there is a current, okay, is supplied to the primary windings, what will happen? Okay, I will generating the H. H will generate the B. From B it will generate the flux. So this flux will then link to another windings which is known as secondary windings. Okay, it will enter this loop, and when it enter this loop, it will generate or it will produce current, and this current, okay, or it will produce a V. Okay, it will produce a V or I. Okay, that is known as VEMF, which is electromotive. Okay, so how did they know? How did he know that VEMF or IEMF is generating? It because they found the galvanometer. Okay, after sometimes the galvanometer is moving. Yeah, okay, it's moving. Yeah, the needles. Yeah, it start to moving. It starts to shows a value. All right. Alright, so this is what are the three observations that Faraday's found, which then becomes the Faraday's law. They said when the battery is turned on, okay, when the battery is starting to turn on, there is a deflection in the galvanometer. And why is this happening? Okay, if we try when the battery is on, if we try to draw the relation between the time and flux, time and magnetic flux, when at an instant when the battery is on, okay, when the battery is on, what will going to happen? It will generate the flux. Okay, flux will be generated, and at some times, okay, at some point, okay, when we keep turning on the battery, okay, the flux that is generated, since that it is a DC battery, it will become a stabilized. Okay, the value of the flux will then become a stabilized. Next, all the flux that is generated then will be linked to this to this loop, okay, which then will move the galvanometer. Okay, will cause a deflections of the galvanometer. And what will happen? The flux inside here, it will then become, if the battery turn off, it will then become reducing. Okay, so this is when the battery is on. Okay, at an instance, the flux will increase rapidly, and it will become stabilized because our battery is our DC battery. Okay, and then it will stabilize, and once the battery is turning off, okay, the flux will then be reduced, and the flux that is generated at the primary windings will link to the secondary windings will then cause a deflection at the galvanometer. So the observations of Mr. Faraday, he said when the battery is turned on, there is a deflection in the galvanometer, and when the battery is turned off, there is also a deflection in a galvanometer, but what will happen? In opposite direction. Okay, in opposite direction. Why is that? Because the flux is start to reducing. Okay, so later demonstration showed that a moving coil will also cause a deflection in the galvanometer, meaning that this, if the secondary windings is now moved, okay, is the secondary winding move, also will cause a deflection. So there are two phenomena. Okay, there are two phenomena that will cause the deflections of the galvanometer. One is when there is the H field that is produced. Okay, when the H field is changing by time. Okay, when the H field is changing by time, okay, the flux will then link to the galvanometer and it will produce the induced force. Okay, or we call it will generate the VEMF. And another reason or another phenomena that also will create this VEMF is by moving the second primary, okay, the second coil. By moving the coil also will cause or will produce the VMF. So as a conclusion, Faraday's experiment, okay, the electromotive force, okay, VEMF or EMF, so VEMF is actually a electromotive force, okay, where the units is given as volt. Okay, so the electromotive force is can be calculated is equals to negative, okay, the differentiation of flux over time. Okay, the changes of flux over time. All right. Okay, so we know Faraday's can be happen ataupun it can be generating when the current is moving by time, which then will produce H that also will vary by time, then also will then generate the flux that also will be vary by time. Okay, so that is the first phenomena. The second phenomena, which, okay, so the first phenomena actually we can write that, okay, flux is equals to P dot ds, right? Okay, so the first phenomena, okay, this first phenomena is caused the changing of field, B field. The B field is vary by time. The second phenomena, okay, the second phenomena is when the ds is vary by time. Okay, so there are two causes of Faraday's law to happen. One, when the our B is vary by time, B is vary by time, and the second one is when the circuit is vary by time, where the ds is vary by time, right? Okay, so in this slide, okay, I conclude the three conditional phenomena that will be produced, okay, that will produce the VEMF. And before that, okay, why there is a negative sign here? So this negative is known as a Lenz's law. So what is Lenz's law basically? So Lenz's law said that induced flux produced, okay, induced flux produced must be always against the directions of initial field direction. Okay, induced flux produced, okay, I try to write here, yeah. Induced flux produced, okay, must be always, yeah, against, okay, against the initial of initial field direction. Okay, it must be always in opposite direction. Okay, with the initial field directions. Okay, so that is what we call as Lenz's law. So that's why it has a negative sign here. So there are three conditional conditions, phenomena that we're able to produce the EMF, electromotive force. Okay, the first one, when the time varying field. So meaning that our flux is producing by the magnetic flux density is vary by time, where the ds is static, the circuit is static. Okay, the field is vary, the circuit is static, and that is what we call as transformer EMF. Another EMF is when the field is static, however the circuit is moving. So if you want to represent, so the flux generated is by the B now is static, the DS now, the circuit now, is moving. Okay, right? The circuit now is moving. That is what we call a motional EMF. Because of the motion, the flux is generated. Okay, so that's why it's known as motional EMF. The third law or the third phenomena is known as both of the field and the circuit moving. Okay, so the flux that is changing by time is due to the B that also change by time, dot product with the circuit that is also changed by time. So this is a combination of transformer EMF and motional EMF, right? Alright, so now let's look at the first phenomena, first condition, which is the time varying field. When the circuit is stationary, or the circuit is not moving, but now the field is vary, which is known as transformer EMF. Okay, so for example, in this case, alright, in this case, the induced magnetic field always against the directions of the initial magnetic field. So this is what known as Lenz's law. Right. So we can see at point 1 and 2, we want to consider how much the electromotive force that is happening at point 1 and 2 when the field, the magnetic field that is applied to this particular structure, okay, to this particular circuit is vary by time. Okay, is vary by time. So what happened? Okay, so due to the closed loop, so if we can see this particular circuit, so this circuit is a closed loop circuit. Okay, so since that this is a closed loop circuit, we are also able to use the theory that we have learned before, where V in a closed loop circuit, E dot dl is closed integrations E dot dl. Okay, where in this formula you have been introduced to you guys when we discussed the electrostatic, right? Electrostatic field. Okay, in electrostatic field, if you still remember, E dot dl, V at the closed integrations E dot dl in a closed loop. In a closed loop, it will be equals to 0. Okay, this will equals to 0 if the circuit is closed loop. Okay, however, in a time varying field, in time varying field, okay, at closed loop circuit, E dot dl will be no longer equals to 0. It will have a value. Alright, so there are two ways for you to measure the value of electromotive. One is by using this formula, okay, where later, okay, on the next slide we're gonna see the relations of this with this. All right, so potential, potential of voltage, potential from point 1 and point 2 also can be calculated by using this equation, right? Right, so now we want to see the relation between the earlier equation, which is the V EMF equations, and also the potential difference equations, right? So from potential difference, we know the equations is closed integrations of E dot dl, all right, which is the potential difference at, if you still remember the circuit, at point number 1 and point number 2, and also the induced force, which is from the equations of V EMF is equals to integrations of negative dB over dt dot ds. So if we equate both of this, okay, 1 and 2, okay, if we equate it, okay, closed integrations of E dot dl is equals to negative integrations of dB over dt dot ds, okay, which is, this is the force of electromotive force equation, and this is from the potential difference equations. So if we can see here, this is a closed loop dl, and this is the surface integrations, right? So in order to solve this equation, we need to convert from this dl into to become ds, yeah. So based on our previous experience, we know that Stokes theorem can convert from dl into ds, right, which is by using the general formula, which is closed integrations of A dot dl will give us integrations of curl of A dot ds. So if we want to apply on this particular formula, okay, it will then become closed integrations of E dot dl. It will be curl of E dot ds, right? Okay, so now we have convert this loop integrations into dl into ds, so it will become as such. So now both left hand side and right hand side now have ds value, all right, ds value, and we can cancel. If we solve this, we can cancel this integration part, and we can cancel this ds part, and only leave behind to us that curl of E is equals to negative dB over dt, and this is what will happen, okay, ataupun or the effect to Maxwell equation when the field now is time varying field. Okay, previously in static field, we know that curl of E is equals to what? 0, right? This is in a static field. But now we have proven that in the time varying field, curl of E will be no longer equal to 0. It will then become negative, equals to negative dB over dt. Alright? Okay, now let's look at the example, the first example. So given a structure as follows. So it's given to you guys the structure of we have one filamentary currents here which carries of IT, meaning that the current is changing by T, and there is also a loop current, okay, with shape of rectangular, which carries a current of I2, where at this area the I is in, one is in a positive Z direction and one is in the negative Z direction, right? And at this closed loop there is 2 ohms, there's 2 resistor which carries of 10 ohm each, and it is placed as a series, in this closed loop. It's given that the loops is 10 centimeter length and is separated with the filamentary current as 5 centimeter. So what the question asks us to find, we need to obtain the value of I2, which is at the closed loop, where given the value of I1 is 2.5 cos 2 pi 10 to the power of 4 T, okay, meaning that the current is changed by time, ampere. Alright, so we need to find I2, Okay, this is our objective. Okay, how much? We're given the current of I1 is as such. So EMF from the electromotive force, okay, EMF can be calculated equals to d differentiates of negative differentiation, yeah, negative differentiation of flux, negative differentiation of flux, magnetic flux over dt. And how to find the magnetic flux is equals to, how to find the magnetic flux is equals to B dot ds, right? Okay, and now our B, the circuit now here is remain. Okay, the closed loop here is remain. So what is going to be changing is, since that the current is changing by time, so therefore our B also will be changed by time, right? So it's going to be negative d over dt, integrations of B that is changed by time dot ds, right? So therefore from here we know B is produced by this current I1. Okay, B is produced by that current. So B is our infinite filamentary. So based on our experience from previous, okay, d over dt, finite filamentary currents will give us mu naught, because B, I1 t, alright, over 2 pi y. Okay, 2 pi y. And what are the directions? The directions were going to be in negative x direction. Why it is negative x direction? We need to recall back, it must be source cross with the point of interest, right? So our source is on z direction, and our point of interest in y direction, positive y direction, right? Okay, this is on positive y direction, right? So z cross with y will give us negative x, right? Dot width ds, right? So ds will gonna be also in the same directions, yeah, dy dz on negative x directions, right? Then from here, if we start to solve, okay, we are able to obtain negative d over dt, okay, the differentiation, okay, and then we can bring the constant mu naught I1t, right, over 2 pi, okay, over 2 pi, and integrations of 1 over y for dy, and integrations for dz. Okay, so what are the limits? So the limits in y directions were going to be from 0.05, okay, the lower limit were going to be 0.05, the upper limit were going to be 0.15. So what is the limit for z? We're going to be from 0 until 0.1. Alright, so if we solve this, we can also substitute the value of I1t with the given value as such, right? So now if we further calculate and continue our calculation, we are able to obtain the value of negative mu naught over 2 pi. It will gonna be negative 2 pi times 10 to the power of negative 4, alright, and then 2.5, okay, 2.5, and sine, yeah, cos integration will give us sine 2 pi times 10 to the power of 4 t, and then integration 1 over y will give us ln 3, and 0.1 for integrations of dz. So if we further calculate, we are able to obtain the value in volts, right? EMF will give us a value in volts over 2 pi, okay, and 2 pi times 10 to the power of 4. Okay, you can simplify this equation. Okay, so please simplify this, try to solve it, how much EMF value that you are able to obtain. Okay, ln 3, okay, ln 3 and sine 2 pi times 10 to the power of 4 t, sorry, t should be inside the brackets, right? T is inside the brackets, so T. So this is given as volt. Alright, so what we want is we want to find the value of I2. So to get the I2, we know based on our Ohm's law, V is equals to IR. So we know the V, we know the R. R is the value of the resistance in series, right? So the value of EMF that we obtained just now, we have to divide with the value of resistance. So since that the resistance is in series formation, so they're going to be 10 ohm plus 10 ohm, we're going to be 20 ohm. All right, and from there we are able to obtain the value of I2t. All right, so the value of EMF is this value, the one that we have obtained earlier, right? Divide with the value of resistance, total value of our resistance, then we are able to obtain the value of I2 in ampere. All right.